thank you for being here. So it is my pleasure today to launch the new series of lectures of prestigious women researchers that we are organizing from the Equity Commission of CITIUS. So I hope this is the first and very interesting talk in a, I hope, very large series of lectures that will extend over time. First of all, I would like to give some numbers because we are scientists, so sort of we like numbers. So you know at CITIUS, the percentage of women in total it's around 20% in global. It is lower, I don't know the exact numbers, maybe 13, 14 if we talk about, maybe even lower for postdoc students. We have also around 20 if we talk about pre-docs, but we have a quite low number of female postdoctoral students, which is not good. On average, for more senior researchers, it's quite okay, but we are lacking women that are coming for the next year. So, I mean, this is something I think we really need to promote, this kind of activities to promote science and women in science at CITIUS. Anyway, the numbers at CITIUS are quite good. If we look at the studies at the University of Santiago de Compostela, we all know the percentage of women in technical careers like computer science, it's about 13%. So it is much, much lower, almost half of the percentage we have at CITIUS. So it's really very, very dangerous. I'm really afraid of what's going to happen in the coming years. If we look at doctoral studies in our doctoral program, it's only 7% of women in our doctoral program. So although we have very quite nice numbers on average at CITIUS, I mean, if we look at what is coming, I think we really need to take care of this and take care of these numbers and think of what we can do to try to improve these things. I would like to finalize my introduction with a positive note. So if we look at the PI, so principal investigators at CITIUS, in the period from 2019 to 2021, the income, so the funding that the female senior researchers at CITIUS were able to acquire, to obtain, is on average 6% higher than that of the male, the main colleagues. So this means that even though we are a small number of women, our activity as PIs is very productive, and it's in terms of funding even higher than that of our colleagues. So I think this is very good news. I think this is something to be proud of. And I think one of our responsibilities at CITIUS is to try to let these numbers be known and let everybody know that we are really compromised with the promotion of women, women's science, and prestigious women researchers in science. So thank you, everybody, for being here. And now I will lead the work to Professor Alberto Bugarin, who will introduce our first speaker in this cycle, which is Dr. Ingrid Zukerman. So please, Alberto.
Yes, just very shortly, because you have lots of information about Ingrid in the bio that is was announced with the lecture, and it's a privilege, it's an honor to have her here. As you have read about her, she got her PhD in UCLA. Many of you know very well about his supervisor, who was Judea Pearl, a very well-known scientist in the field of adjacent networks. So this is a clue about how one of her research areas that has been and is still adjacent networks, and more recently explainability in adjacent networks, which is a topic which is quite interesting and relevant for us. But she is also very active in the areas of explainability and in general data science and on artificial intelligence, because she's a professor in that area at Monash University. So she will talk us today about decision trees, explainability. Again, these are very well-known topics for all of you, so I'm sure that we will enjoy her talk. Again, as we said before in the seminar, we have the are very lucky to having her here for 3 days. Also, Ehud will be with us today and tomorrow, so feel free to reach her, to talk to her, to chat with her, and make this opportunity of meeting them in person a nice contribution for your training, for your information, and for everything you need. So thank you very much, Ingrid, for coming here. It's a pleasure. So the floor is yours. Thank you.
Thank you. Yeah, it's great to be here. I do colloquial Spanish, but technical English. So yes. So what I'm going to talk about is recent work that we did with Samin, Ehud, who's here, and Reza Hafari. And this work has been published in another paper in the same issue as Ehud's paper in computer speech and language. But I don't have the URL. Sorry, you can ask me. Okay, so what we are going to do is we're going to talk about context, the influence of context in generating explanations and in users' views about explanations. So the aim of this project is about generating post hoc interpretable explanations for specific outcomes of a transparent machine language model. And you see a lot of underlying things there, and we're going to drill down into each of those things. Is it? So post hoc, we are going to explain after observing a model's results. What is interpretable? This is Miller's definition. Interpretability is the degree to which an observer can understand the cause of a decision. What is a specific outcome is an instance. So we're not explaining the entire model, we're explaining a particular instance. And what is a transparent model is transparent models are interpretable by an ML expert or a statistician. So transparent models are decision trees, logistic regression, linear regression. And you will ask, why aren't you explaining deep learning? A, because it's harder, and B, because people actually have used transparent models to approximate the decisions made by opaque models. So starting with transparent models seemed like a good idea. And now I want to drill down into these two concepts. Who is the observer, and is that all we are doing? Are we just understanding? So here we are again with those concepts. And we are aiming our explanations at non-expert end users. So some type of decision maker that is receiving the output of an AI. And what is the context? We are considering two types of context. One is background information. We are trying to take into account the background information that people have. Now you are going to ask, but different people have different background information. So we get around it, we control it experimentally. The domains are so particular that nobody should have a lot of background information about them, and we give them what they need to know. Now, users' goals. So Miller is talking about understanding. However, there are other goals. So we are considering three goals. Understanding, indeed, but there are other goals, changing an outcome. So if you have an undesirable prediction, you want to know, how can I change it? Retaining an outcome. If you have a desirable prediction, you want to know, you want to do some sensitivity analysis that says, what can I change and still keep this? And there are additional goals, like scrutability, like can I inspect the correctness of the machine learning model, trust, decision making. So we are focusing on those three. So the talk is divided in two parts: background information first, then user goals. So we are starting with the background information, and our domain is a nursery school. kindergarten. So this is a data set obtained from Olave et al. It's a data set about a nursery school in Slovenia, and it's a charity nursery school. So people with difficult circumstances are preferred, some type of difficulty in their circumstances. And there are 3 outcomes: reject, waitlist, and priority accept. Priority accept is really accept straight away. And this is a sample of background information. So you give the profile of a child, and you give this information about their situation. What is the parent's employment? What's their current childcare conditions, housing conditions, social situation, and health. Who makes this assessment? Social workers. So we have, if you're interested in the paper, in the appendix, there is a rubric provided by the social workers that I explain each of these concepts. And what we tell the users of our experiment, and you, is what happens for each of these cases. For example, if the parent employment is challenging, 34% of the applicants are rejected, 20% are waitlisted, and 46% are priority accepted. And these are the priors. So it's basically 1/3 each. 1/3 is priority accepted, waitlisted, or rejected. So this is what users see in our survey, and this is their background information. Yeah, all good? By the way, Alberto, what's the protocol? Can they ask questions in? Yeah. Sure. No, if you're curious, please ask. Oh, this is it for the. This is one child. Oh, several values. There are there are different numbers of values, like between. Oh, this is several outcomes for this feature. This, like not for this child, but we are telling these are the features of the child, and if you look only at this one, these are your percentages. Patience, my dear. Okay. Okay, so our decision tree is using only these 3 features in this particular branch for this child, and this is our sample explanation for this particular child, and it includes 2 parts: a preamble and a resolution. So what is the preamble? The preamble is the part of the explanation that addresses the context provided by the data. So it says, from the data, one might expect the children with good current childcare, this one here, will be a great deal more likely to get waitlisted than to get a priority acceptance, 54% versus 11. So you say, if you are just looking at the data, this is what you might expect. And now we give you the outcome. However, the AI system has learned from the data that among children with challenging parents' employment and average health, those with current childcare are almost certain to get a priority acceptance close to 100%. So the idea of these explanations is identify something that people might expect upon seeing the data, and then tell them what really happened. Now, we are not saying that people will expect this. We don't know what people expect. We're saying, but if you look at this, it is reasonable that you might expect this. And this is what we are addressing. Okay, so now how do we do this? So, as I said, we want to address potential conflict. between plausible expectations and the decision tree prediction. And we have two basic type of conflicts: expected outcome and predicted outcome. So you think somebody will get priority accepted, but they get waitlisted. And also there is a conflict about the expected impact of a feature value. You think that something will be very important for the prediction and then wasn't so important. So you identify this conflict. You select one feature that yields a conflict. Like you saw before, we were talking about the challenging parents. No, what were we talking about before? Sorry. The childcare. You select the feature, the childcare, and then you realize the explanation. So these are the steps. So now we're going to talk about how we identify potential conflicts. So the first conflict is about expected outcome. So you expect a particular class and you predict a different class. And we have identified two types of this conflict. One is a feature value. Xij is value j of feature I. Licenses an expectation for you not getting class C, so any other class, not C, but you got C. So in our case, you are expecting reject or waitlist, and you got priority accept. And the other one is a particular case. You are licensing an expectation for C max, the class that has the highest posterior probability given this feature, and you still got C. So these are two outcome expectations. The other one is an impact expectation. So you license an expectation for C. C is predicted, but the variable has no impact. And the last is a combination. You have the expectation doesn't work out and the impact doesn't work out. Nothing works out. And then you have, so you license an expectation for not C, you predict C, but Xij has no impact, and you license an expectation for C max, C is predicted and no impact. So these are all the cases. Now, this is where I jump on my sword. For some reason, we thought this wasn't important and we never included it. It seemed a good idea at the time. So yeah, so this is what we are investigating. And now I'll go into the details how we do some of these options. So the first one is, how do we detect that you are expecting not C? So you have two conditions. The posterior of the class, given this particular feature, so what you get from the table that we see, that we show people, is less than or equal than the prior of this class, and it's less than the posterior of not C. Those are your conditions for expecting not C. And you get a preamble. Again, we're in the preamble part that we are explaining what people will expect, or not people, but what are plausible expectations. From the data, one might expect the children with critical current childcare will be less likely than applicants overall to get waitlisted. So I think we're expecting anything but waitlisting. Okay? The next one is C max. So it's like not C, but more specific. It's not that you're saying that C won't happen. You're saying something else will happen. So now you have more conditions. So what have you got? The posterior of C given a particular feature is less than or equal to its prior. The posterior of C max is greater than its prior given this feature. The posterior of C max is greater than the posterior of C, because you are expecting C max, and the posterior of C max is greater than everybody else. This is your maximum expectation. And now you say something like this. From the data, one might expect that children with good current childcare will be a great deal more likely to get waitlisted than to get a priority acceptance. And that is that line in the table that was highlighted. And I won't explain the combinations in the interest of time. This is the last one. So this is the impact. You expect Xi to have an impact. So you're saying the posterior given Xi is greater than the prior. The posterior given Xi is greater than the posterior of all other outcomes. And this one says, whatever it is that what the feature that you are picking, Xi, should not be the weakest link in the DT, in the path of the decision tree. It shouldn't be the feature that gives you, there should be at least one worse feature in the path of the decision tree. It would be odd if you pick the weakest link. So here, this is very similar to the other explanations because we don't know what's the resolution. But you are saying from the data, one might expect the children with challenging parent employment will be more likely than applicants overall to get a priority acceptance. Okay, this is your expectation. We're not saying what's going to happen. So before we go, okay, no, a few more things before we go into anything. So how do we generate those phrases? We rely on the work of Elsasser and Henrion, 1989. Nothing better has come along since. So there were things that happened before you were born that were useful. Yeah, so they did some research where they compared probabilities, and they did to elicit relative phrases. So what we have here is, for example, if the posterior of waitlist given current childcare is here, 054, and the posterior of priority accept is here, then you can generate a phrase such as waitlist is a great deal more likely than priority accept because we are in this quadrant of the, not this region of the graphic. And they did user studies and they got agreement, 76% agreement, so good enough. We did a small pilot with this, and for us, it turned out that people were not that fond of this distinction and that distinction, and we just called it more likely or less likely without somewhat and a bit and those things. Okay, so this is where we are at. Now, how do we select? Now we are in the next step, selecting a feature that yields a conflict. So if several features qualify, we want the strongest in terms of word mapping. So if you can find a great deal more, you pick it rather than more. That's one thing. And the next thing is, if you have a tie, then the tie-breaking rule depends on the conflict type, and this is only one tie-breaking rule, that if you have several that are a great deal more, pick the one with the maximum difference between these posterior probabilities. But don't worry if this is getting a bit hairy. So, and please keep in mind that we are not deciding which conflict, which type of explanation we're generating. This is the purpose of the user study. We are presenting all the explanations that we can generate. But we need to pick one feature, and this is how we pick it. So finally, We realize our explanation. So the basic explanation, which is our baseline, follow the path in the decision tree. And the conflict-based explanation, which is what we do, gives the preamble and the resolution. So the preamble presents the plausible expectation from this feature, and the resolution describes how the expectation did not happen. And now we can do a few examples. So the first one is what happens when we are expecting not C and predict C. The preamble, it says, from the data one might expect the children with critical current childcare will be less likely than applicants overall to get waitlisted. However, the AI system has learned from the data that among children with ordinary parents' employment, somewhat problematic social situation, and good health, those with critical current childcare are almost certain to get waitlisted. So this is your preamble, your resolution. And one thing I forgot to mention is that the feature values are color coded according to how bad they are. Red is bad, blue is good, and purple is in the middle. So are we clear on these explanations? Yeah. No, good for the child. The child is doing well in that respect, as evaluated by the social worker. Yeah, it's coding the opinion of the social worker. Then Cmax. So again, from the data, one might expect that children with good current childcare will be a great deal more likely to get waitlisted than to get the priority acceptance. And there we go again. However, the AI system has learned that challenging parents, average health, if you have the good current childcare, you actually do get the priority acceptance. So basically, this is what people get from the table, and this is what they get from the tree, which is different from what the table suggested. And finally, this is the no impact one. Again, you are expecting to get the priority acceptance. And now we get this one. However, the AI system has learned from the data that the parent's employment has no effect on the outcome, and that children with very critical current childcare and good health are almost certain to get a priority acceptance. So here you get the outcome that you expected, but what you don't get is that parent employment has any effect. Okay, so this is where we are at. Any questions?
I mean, for example, if you have the tree, you can look to the confusion matrix of the classifier and see this class is more likely than the other. Depends on the training data that you have. And you say, according to the data, so this could be only looking to the data distribution, not to the model that was learned from.
What we told people, we gave them this table with data. This is their background.
That is what you show to the evaluators, to the participants in the survey.
Yes, study. And then you say, it would be reasonable to expect this based on what you saw. And most people would have no background information about childcare in Slovenia. And
yeah, but exactly where is this background information coming from?
From the data set from Slovenia, yeah, so that we present to the users. Okay, evaluation. So research questions. How do conflict-based explanations compare to basic baseline explanations? And these are our attributes: completeness, presence of extraneous information. They are coded based on desirability. So extraneous information is misleading, contradictory, irrelevant information, bad things, helpfulness for understanding the AI's reasoning, enticement to act on the prediction, and preferences, which is what do you prefer, that's why this guy is neutral. And second, which independent variables influence users' views of the conflict-based and basic explanations. What are our data sets? We have the nursery, that is my favorite one. So that's why I talk about it. And telecom, which is a decision tree, predicts whether a customer will churn, leave a company, or stay. And we conducted one experiment, one study with each data set. And what is the experiment? Users saw a sequence of scenarios in random order, and each pertaining to a different family or customer. Then for each scenario, users were asked to predict the outcome. And after reading the prediction, they received two explanations, basic and conflict-based. And here is what it looks like in Qualtrics. And so we have an applicant. By the way, as an aside, initially we were very inclusive. We had names from people of different ethnicities, and we were told, cancel all Anglo names. Why? You don't want to preempt judgment based on ethnicity. Yes, we live in an imperfect world. And so they're all Brown and Smith and whatever. Yeah. So this is their application. These are the features. They get the data on the basis of the features. And they get the prior probabilities. And as the director of the Bilby Child Care Center, what is your expectation regarding the outcome? And you click. Bilby is a small Australian marsupial. And yes, if you're interested, I have a picture. Yeah. And so people click on their expectation. And then we tell them what really happened. Based on the Brown circumstances, our AI system predicted their child will get a priority acceptance. And now we show them the explanations. It's a bit small to see, but the sides are randomized, but all the users see the same sides for a particular scenario. And we have 4 questions: complete, misleading, contradictory, or irrelevant information, helps me understand the reasoning of the AI, and would I perform the action predicted by the explanation? So, and these are 2 explanations, the conflict-based and the basic. They see them side by side, and they also indicate their preferences. Our first platform was Sona, that probably nobody has heard of. It's a platform used in business economics and psychology. It's popular in Australia, I think in the US too. And it was quite painful to use because we were very slow in recruiting participants. They would drop out. It was difficult. And you see here the genders. So the red numbers are the ones that had majorities. And yeah, so, well, this was, and you see that it is kind of a bit self-selecting if you look at gender, because the topic of the experiment was advertised in the recruitment call. So we said, this is an experiment about nursery school. This is an experiment about telecom. And the preferences are obvious. So here we go back to our research questions. And So these are our results. And you see that for nursery, conflict wins in 3 out of 4 of the explanatory attributes. And for telecom, conflict wins in terms of completeness. Now, these are all statistically significant results. And so where there are no results, it means same statistically. So yeah, we were happy. And then we have this one, preferences. So in the nursery, in both cases, the conflict-based explanations are preferred, but in the nursery, it seems stronger. The ratio of preferred to dispreferred. And in terms of relative preferences, all our comparisons are conflict versus basic. We didn't compare between conflict-based explanations. So this is our suggestion based on preferences. So Cmax, expect Cmax and predict C seem to be the most popular. Then expect not C, predict C was the most popular. Then this one, expect Cmax, predict C, no impact. Now, oddly enough, this was a clear winner for nursery, and for telecom, it was kind of even-steven. And people didn't like this one at all. Yeah, and this is a bit odd because it actually conflicts with the results of Biran and McEwen from HCAI 17. Now, the last thing, independent variables. There were several independent variables that we had, but the only one that could be examined was predict versus expect. So disagreement between, just for curiosity, the other variables were predicted outcome, selected feature, and explanation length, and predicted outcome and the feature that was used in the explanation are domain dependent, so they don't give generalizable solutions. And explanation length could not be used because the conflict-based explanations are always longer than the basic ones. So predict versus expect. Now, in 1/3 of the cases, people did not get what they like the expected outcome. Like they had to say what's going to happen. In 1/3 of the cases, they were wrong. So we tried that. And this was kind of cool. Because one thing that you see is when people did not get what they expected, this one goes away. They only feel that the explanation has extraneous information when they got what they expected. So why are we telling me all this palaver, right? But if I didn't get what I expected, no, I want to hear your palaver. And in terms of overall preferences, conflict, 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 and same. We were very happy. Okay, moving on. Any questions? Because we're moving on to users' goals. Okay. So start with our data set. Our data set was the Busselton data set. It's a town in Western Australia that it has 2 claims to fame. It was the 2nd longest jetty in the world. And they did this study in Busselton. And this study was done in the 70s, so the data is not up to current medical knowledge, even though the date says 1998. So predict the person's risk of coronary heart disease. How did they do the study? They collected information about the person, and then they saw if they died of heart attack up to 10 years later. And then the predictions are based on that. So the predictions are not based on any deep medical insights, totally on data. And 2 outcomes, high risk or low risk. And we have much more features here. So for example, this is a particular instance, particular patient. So cigarette consumption, alcohol intake, HDL cholesterol, age. Most of you are not worried about any of these things. And so this is what people get to see about the patient. Again, color-coded for desirability of the features. And here is a sample explanation for this patient. The prediction was made because the AI system has learned from the data that people who are between 43 and 60 years old, smoke between 0 and 28 cigarettes a day, have an optimal level of HDL cholesterol, are at a low risk of a coronary event. Okay, that is your prediction. And let's give you a goal. You want to retain this prediction. Yeah, you don't want to die. And then what happens next? Users could select a question, what to ask next, given that they had this objective. So a popular question was, which factor changes will result in the same prediction for me? So they want to keep not dying, but they want to know what they can change. And we would generate something like this. If nothing else changes in your circumstances, the following would result in the same prediction for you. Any changes in one of these factors. So these were factors that are either not in the path or in the decision tree, or your HDL cholesterol changes from optimal to borderline. So I will go into how we generate these explanations. So as I said before, we are considering 3 goals: understand, change, and retain. And the influence of the goals is seen in 2 things. One, the questions that were selected and what people thought of the system's answers to these questions. So the approach used in the experiment, it was an immersive experiment. I don't know how well the immersion worked. They were asked to pretend that they are the patient. So users are given an instance and a basic explanations. They are given a goal. Now, why are we giving them a goal? Because if you let people choose goals, you cannot control the experiment. So they have to be given a goal, but the goals were sensible. And they choose follow-up questions for each goal and assess the answers. And there are 2 types of questions that we had. These questions were sourced from Liao's data bank of questions. Now, we have to basically constrain these questions for 2 reasons. One is that you have to let, if you ask people, well, actually, one main reason, if people type in open-ended questions, you may not be able to answer them. Like, you don't have algorithms for them. And second, you can misunderstand the question. You introduce problems into the experiment. So we picked these questions from this bank of questions. And these questions are general questions. What factors were used by the AI systems? By the AI system, what factors were not used? And instance-specific questions. Again, narrative immersion. You are the patient, so these are reasonable questions like, why wasn't the other thing predicted? Whatever was the other thing. So if you were predicted you are going to die, well, have a heart attack. Then why wasn't I predicted not to get one? Or whatever you were predicted, it was the other thing. How to get the other thing, whatever is the other thing. So it wasn't just go from bad to good. You could pick the other thing. How to still get the same thing, which is what we saw in the example. And what if I change one factor? And then you had to select the factor you want to change. And Alberto, how are we going for time? We started a bit late, so tell me what I got. 15? I can do 15. Yeah. Yeah, okay. Okay, so now we are going to go briefly into how we generated the explanations. What factors use? You just collect all the features in the decision tree. So in general, the following factors were used, and you list everything in the decision tree. What factors were not used? So you take all the features in the data set and you subtract those in the decision tree. So the following factors do not improve the accuracy of the AI's prediction. So we are actually saying why we didn't use them, and hence are not used by the AI system: blood pressure, triglycerides, and diabetes. Surprising for people who know about these things, but nah. Okay. For the next explanations are about specific instances. So this is one of the patients we gave them. I draw your attention that for once being male is bad news. And yeah, the ladies are smiling. Yeah. Yeah, so this was one of the patients. And okay, what's your prediction? What? Highly probable. Yes. Sorry. And here is the explanation. This prediction was made because the AI system has learned from the data that men, in red, who are between 43 and 60 years of age, have high total cholesterol and borderline HDL cholesterol, are at a high risk of a coronary event. So this is where we are at. We've gotten our explanation. And now we are going to go into how we generated a few of the options. So if you are asked why not C prime, so why didn't I get low risk? We select the node with the largest drop in probability for class C prime, low risk, in the DT path. So in this case, this is the decision tree path. So if you are at this age, you are at 80% of low risk. If you got next step 75, next step 0.6, oopsie. Yeah, 0% probability of low risk. So this is what you get. The AI system has learned from the data that about 60% of men who are between this age and have borderline HDL cholesterol, so up to there, up to here, are at a low risk of a coronary event. However, because you have a high total cholesterol, the AI system predicts that you are not at a low risk of a coronary event. So this is your highest drop from 0.6 to 0. So this is how we generated those explanations. Now, the next one is how do I get the other thing? And for each path that leads to the other thing in the decision tree, list a set of feature values that differ from those in the current instance. So if nothing else changes in your circumstances, the following would result in a different prediction, low risk of a coronary event, for you. So this is your total cholesterol changes from high to borderline normal or low, or your HDL cholesterol changes from borderline to optimal. And this is how you get the low risk. And I'm going to skip the how to still get C in the interest of time. And what if I change one factor? And there are three options here. You can change a factor in the decision tree path, you can change a factor in the decision tree, not in the path, and you can change a factor not in the decision tree. And all the explanations are different, but I'm only going to focus on this one. You change the factor in the path. And okay, before I do it, what we do is we look at only this factor that the people nominated and split the explanation based on whether a change in this factor resulted in the same prediction or a different prediction. So say the user selected HDL cholesterol, so same prediction. If your HDL cholesterol changes from borderline to low, it would result in the same prediction for you, provided nothing else changes in your circumstances. And however, if your HDL cholesterol changes from borderline to optimal, it would result in a different prediction for you. So this is, and as I said, there are other flavors of changing one factor. Empirical evaluation. Again, research questions. How does the goal influence the selection of follow-up questions? So what are the most commonly selected follow-up questions? And do the selected follow-up questions vary with the goal? I should have asked you before if you have any favorites for most popular follow-up questions, but by now you have forgotten what they were. So, and now, how does the goal influence users' views of the answers to the follow-up questions? And we have completeness, again, presence of extraneous information, usefulness for the goal, and need for additional information. And again, which independent variables influence users' view. Data set, as I said, Baselton. Experiment, users saw 3 patient profiles in random order, and each was associated with a goal. For each profile, users were asked to predict the outcome. Again, after reading the DT prediction and the basic explanations, users were given a goal and they had to go through 3 rounds of selection of follow-up questions. They could do more if they wanted, but only very few of the users did more. I think it was 11%. Or, sorry, 5%. Yeah, so, and again, users were given a goal after all of this, main reason being that the basic explanation was not affected by the goal. And if we gave them the goal before they made a prediction, they would realize what they should predict. So they were given their goal at the first possible moment, that it wouldn't affect the experiment. Oh, and this is now, this part, after we submitted the paper to the journal, we repeated the experiment so that we could associate each goal with 2 profiles. And we thought then we will have the result if the paper gets rejected, but it got accepted. So the journal only has the experiment with 1 goal per profile. So here is the Qualtrics experiment. We have this patient. Assume that you are a 58-year-old male who is overweight, does not drink and does not smoke. However, you have normal to high blood pressure, high total cholesterol, borderline HDL, and borderline triglycerides, but on the upside, you are not diabetic. If you hover over the mouse, over the underline, if you hover over the underlying values, you will see the range. And you also, in the introduction, if you hovered over the concepts, you could see an explanation of what the various concepts meant. So, and now it says the AI system will make a prediction, but first, please indicate your expectation. So you could make your, based on your profile, the AI system predicts you at a high risk of a coronary event. They get the basic explanation, they're given the goal, and they're asked the first set of questions: completeness, irrelevant, misleading, contradictory, useful for my objective of understanding, do I need more information? Oh, and here are the follow-up questions. So now you can decide what is your favorite question. So general questions and specific questions. Decided? What is your favorite question? In general. No, like, keep it to yourself. Don't tell me. Okay, you have. So for our example, I'm going with that question. Why wasn't I given a different prediction? And this is the same example we saw before. So you pick the one that causes the highest drop in the probability of a different prediction. And here we have a few more questions. Well, first we ask, have I addressed your question? And the second thing, we have here an attention question. So we sprinkled attention questions all over the experiment. We use cloud research, as I mentioned. We had several reasons. One, that SONA was very slow. Second, SONA only gave us Australian participants. And we thought we'll go for a more varied pool of participants. And you could also specify age. You could specify all sorts of things. And one thing we asked, the level of concern about coronary event. We wanted to know if that would affect their questions or something. And very weak correlation with anything. So their level of concern did not affect anything. Okay. Now, what are the commonly selected questions? Okay. You see who was the winner? How many of you were right? Okay. So no matter what was the goal, this one was the winner. Now, how did we do this calculation? We computed the steady state probabilities in a Markov chain. So what happened was that what we did was that every time a question was selected before another question, we increased its probability. So the probability is who was selected before whom. And then we put it in a Markov chain, computed steady state probability. And here I'm giving you the top 3. So this is very interesting that no matter what, people want to know how to get the other thing. The other ones are pretty obvious. So to change, you want to say, what if I change one factor? Why not C prime? For retain, you have how to still get C. Pretty obvious. This is still a bit not obvious. So what if I change one factor was pretty popular. The other thing that we did was we wanted to know what was the overlap between pairs of goals. And for that, we computed rank biased overlap, which is for each user, we calculated for the first 3 questions how they matched for each user and each goal, how the first 3 questions matched, the order in which they were selected. And you see that there is some overlap, but it's not huge. So the goal does affect the order of selection of questions. Now, what about users' views of the answers? The main goal that made any difference was changing. For the other goals, none of the explanatory factors had much of an effect or any effect. So for the goal of changing the outcome, we see all of these. The answers to all of these are considered more complete than the basic. Extraneous information, no difference. The answer how to get C was considered more useful than anything for the goal. So people really love that one. And need for additional information, these ones required, they were considered better than basic, so they required less information to achieve the goal. And independent variables, so whether the explanation addresses the question, so no surprises here. If it addresses the question, it's considered complete, it's considered useful, and it does not deemed to have irrelevant information. No surprises for selection round. The further along you are, the less information you need. Explanation length, longer explanations are deemed better. Now, we have to take any results about length with a grain of salt because according to Lombroso, people think longer explanations are better, especially when they include jargon. So they just think, oh, if I'm being told more, it's probably a good thing. So this is the end, conclusions. So what if I got to tell you conflict-based explanations are a good thing? So include them. There is no reason not to. Users' goals. Yes, the goal affects what people want to ask for first. How to get C prime, how to get the other thing is the most popular, and it's rated better than everything else for changing the outcome. So here we have some guidelines for offering additional information to users. Limitations. The data sets have relatively few features. So for the background, we only had one conflict feature, and we didn't perform any feature selection. So Adarsa over there has investigated a different decision tree algorithm that makes very concise decision trees, and then it will reduce the need for feature selection. This is the next thing I want to do with my life. We told people we were always right. And obviously we're not. So the next thing is to investigate what is the effect of uncertainty on people's views. The common knowledge is that the moment you offer uncertainty, people are less inclined to follow your advice. So, yeah. And limitations of the experiments, we used crowd workers, so nobody had skin in the game, even though we tried narrative immersion. They wanted to get paid. And in the goal experiment, we only had 2 profiles per goal. The profile didn't have much of an effect, but it did have some. So if somebody were to replicate, they need to do additional profiles. And that's it. Thank you.
Yes, thank you very much, Ingrid. So time for questions. So please, your questions through the mic for the streaming. Any question, any comment, remark? Please.
Thank you, Ingrid. Very interesting talk. And my question is regarding the questions for the explanation. So you have presented those about what I have to do to change the outcome. Okay. Did you did any research regarding this question? What happens if the context change? So in this case, do we need to retrain the model, or could we provide some explanations? I mean,
You go with the tree. Like your whatever is your training, if the tree gives you some nonsense, then yeah, actually we in our experiment, the tree did give some nonsense, and we removed those cases because we couldn't possibly. And this is reported in the paper that yeah, because the tree is not medical, it's statistical. For example, in one of the branches, if you gained weight, you had less risk of a heart attack. Yeah. Obviously, this is for this particular population in Basildon. This is what turned out after 10 years, but this is not medically responsible. So we could not present it. So yeah, whatever is in the tree.
Okay. So the context is in the tree.
Yeah.
Okay.
So thanks for the very nice presentation. One of the messages that I got is that counterfactuals are very relevant, like how to get C prime. I know that for answering how to get C prime, there are many possible answers. Do you have any insight on how to rank different counterfactuals that might come out from the tree?
The first thing is I'm going to be nitpicky.
Yes.
I apologize. These things are called by people who are more nitpicky than I am. They're called transfactuals.
Transfactual.
Yeah.
Why?
Because counterfactuals are about the past. If I had done this, what would have happened? The past is the past. You're just transfactual is how do I change the future? So a lot of people conflate these concepts and they're very happy. But once I read about transfactuals, but I'm going around your question. Yeah. So we gave all the options from the tree, but we cheated in the sense that we did not talk about age and gender. So, well, first of all, nobody knows what's the effect of changing your gender on your cholesterol, on your heart, because we don't know,
No, yeah.
Yeah. But age, like say if you're 58 years old, actually the tree says that if you are a male and you're over a certain age, you're going to die of a heart attack. That's it. You're done. Yeah. So yeah. So for example, we did not include age to make the explanations shorter, but also
because you can't change it. It's not an actionable
no, but you can.
change.
If you're 58, you're going to be over 60 in 2 years.
Ah, yeah, that's true.
Right?
You can only change in the future.
Yes.
Okay.
So we circumvented that issue to keep the explanations short. Once we got rid of age and gender, all the explanations were manageable, and we could include all the factors.
I see. But
right, so we skirted around your issue.
Okay.
What would you include? I mean, you cannot lie to people. If they ask you what are all the changes I can do and still not die of a heart attack, you cannot say, oh, do only this and that, and maybe there are other things.
Yeah.
The trivial example is here are a few, and click here if you want more. That's trivial way to deal with it. A more intelligent way to deal with it, but that's a bit presumptuous, is to say what changes are easiest for people. Like say, for example, if I tell you to diet or take a pill, I'll take a pill any day of the week, right? Yeah. So, but then life gets complicated. Depends on people's priorities.
I see.
Right?
No.
So, is that what you were asking?
I partially answer other curiosities, but my question was more regarded to, let's suppose that the trees tell me that there are 100 ways that I can change the prediction in a
Transfactual, yeah.
way. I guess you have to pick one or two to show at the beginning. Did you have this problem of having many
we got
to show?
around it. When say for example, when it was changing a feature, say from low HDL cholesterol to borderline, optimal, high, whatever, right? Then you just list all of them. Your HDL cholesterol could change to any one of these. So we put them together, right? And then you could say, or this other thing, or the next thing, So we had a few ors, but we tried not to go crazy.
I see.
Right?
Makes sense.
But it's an artifact of the tree that we had, of getting rid of age and gender.
How big was the tree, by the way?
How big was the tree? A good question. 64 nodes, if I remember correctly.
I see.
I can check. I may be confusing it with nursery. Let me check and get back.
No. See, but decently complicated. I mean.
Yeah. This one was far more complicated than nursery.
I see.
But yeah, maybe 64 is right. But I'll double check. So yeah, we circumvented the issue. But if you have to pick, you run into ethical questions. Which ones and why? That's why I'm saying pick a few and then say click more if you want to see more options.
Makes sense.
That's the most decent thing to do.
Thank you.
Maybe it's also it's quite interesting to see this overlapping between explanations and recommendation, because it seems that what's relevant for users is not in many cases to get an explanation, but to get what to do in the future in order to change from a diagnostic to a better one. So within this overlap between explanations and recommendation, maybe it could be interesting to gather more evidence that this is what really matters for users, because maybe it's quite interesting to know, for example, if this happening only with diagnostic, with things that threaten your life, for example, or if it's happening in the both directions. For example, if I get a good diagnosis, for example, or I'm in good condition, what will be my interest? To keep it even better, or just to keep?
Well, everybody asks how I get the other one. Yeah. Even if you got the good diagnosis, they want to know, and how do I die? Yeah.
It was in the two directions.
No, everything was in two directions.
But that's fairly surprising.
I know.
So maybe getting more evidences in different experiments in that direction could be quite relevant, because somehow with these recommendations we are entering what medical professionals do, which, as you mentioned before, they try to do a recommendation which is practical, which improves your health, but can be done by you with not too much effort. Getting a pill is much easier than other options, and for some people it may be the only option. But so this idea of what's preferable in order to improve the diagnosis is quite interesting. So among these hundreds of options, maybe medical or domain knowledge about which is the best way to recommend will be also interesting to include in these explanations.
But also patient priorities.
I don't think medical professionals care a lot about that. Maybe they assess globally, they see people will stick to the weekly pill or not. They will gather a lot of information, some feeling about them. There are lots of issues involving, which is related to knowledge about what and how give the recommendation, and which recommendations could be more effective. So probably there's a research area there. Yes.
A quick comment about the models I saw in the paper. They are quite small, 43. There are 47 nodes in one of them. The other is 47, 41, and 36 in the three data set that you have.
Where did I get 64? Sorry.
Well, anyway, apart from that.
Which one? Well, since...
it's in the appendix of the paper.
Yeah, I know it's in the appendix, but what was the Baselton? What was the size since you got it?
The Baselton, that is the low risk, high risk, this is 36.
Okay, I wasn't too far.
20 leaves and 36 nodes in all the three.
Yeah, okay. Thank you. I appreciate that.
Well, apart from that, I wanted to make a comment regarding the counterfactuals that in most of the literature, people think about the minimal change in order to change the output. And for that, we noticed with many experiments that we did that sometimes we got this that you say, we get that the closer branch in the tree that will activate it to give the other output, sometimes it's not meaningful. And this depends on the accuracy of the tree a lot. For some of the data set that we deal with, when the data set is really well, let's say easy, and you can get 90% of accuracy, then this makes sense. But we have some data set with diabetes or thyroids that is around 70% of accuracy in the data set. And when we start to make explanations, there could be more and more explanations that were making no sense, especially when dealing with counterfactual or transfactuals or whatever, because
really?
it appears this type of things like if this feature were higher, then you change the effect. And you say, this makes no sense from my point of view, but it's because the data set statistics are reflecting this future impact.
The thing is, with the changes, we are writing another paper with the student, and that is about cars. So, for example, there the counterfactuals are, what do you give for counterfactual? Those are real counterfactuals. Like you say, this car is deemed unacceptable because, say, the price is too high. And then you say, what is your counterfactual? Do you want to change a lot of features a little, or do you want to change one feature a lot? Both of them will get you the other outcome, but it depends on the person.
Yeah, that's, I agree, is the answer to Alberto about the preference, not only the doctor, but the preference of the patient. And this is related to medical adherence, for example, because the physician could say, well, this is the optimal thing. You have to go with this therapy, take this pill 3 times per day, and then your habits make it impossible to follow that. And then you prefer something that is an alternative that is easier for you to follow the treatment.
Yeah, one thing for those of you who are interested, I've been reading this book, bedtime reading. It's called Reckoning with Risk by Gerd Gigerenzer. I wasn't prepared. And they talk about all these, he talks about all these issues about do you involve patients in your recommendations? His main point is that doctors don't know probability. But in addition to that, all these, he deals with all these issues about how to inform probabilities, how to enable patients to participate in these decisions. It's a very light read, so definitely bedtime reading. So I recommend it. A bit repetitive, but still okay.
Okay, there's no more questions. So thanks you for letting us know that we will die soon from a heart attack. We appreciate that very much. So thank you very much for the night talk, and hope to see you here again physically soon. Bye. Thank you.
Bye.